finally been around the school long enough to actually recognize the faces in here, which is cool. I'm Justin. I'll be your guide to the computer graphics world for the fall semester, should you choose to stick around, and I certainly hope that you will. We're here to talk about computer graphics, so I thought, especially since students always show up late on the first day, we'd start with a very important video clip, which is historical in the computer graphics world here. My hope is also to test the audio in this classroom. Okay. How many of us have seen this little short film before? Just a minute. Yeah. Wow, not that many. Huh. You guys see when this video clip was made? 1983, I believe. 86, rather. Yeah. So essentially, to keep things short, in our graphics class 6837 this semester, I think you guys will basically learn all the tools you need to produce Lutzo the Lamp, this video, and in much faster rendering time than probably John Lasseter experienced in the 1980s. Pretty much watching you guys watch this video is really one of the fun parts of being in computer graphics and the research and engineering world, because this is one of these fun disciplines that's right at the intersection of really heavy-duty technical challenges and emotion and expressiveness and art, and really coming up with the right technical tools for designing a lamp that can somehow communicate emotion to everybody in this classroom, I think is just this amazing development in the computer graphics world, and one that I think we take for granted a little bit today. Of course, in the 1980s, when they saw this was the first, I think the first second short film that Pixar produced. Before that, they made advertisements for a little bit of time and sold hardware. You know, they started as a hardware company. And I think the rest really is history, right? And obviously, even though computer graphics technology has progressed quite a bit since the 1980s, the basic techniques that were already being used then really are pretty representative of the pipeline that we'll learn in this course. So our plan for today is to give a quick overview of the computer graphics world, kind of see what you guys have in store for the semester here. Then we'll cover everybody's favorite administrative information for the semester, talk about grading and assignments, all that fun stuff. And give it a quick overview of the assignments, which also kind of parallels our overview of the computer graphics world. And then with what remaining time we have, we'll talk a bit about OpenGL. Out of curiosity, how many of you guys have written OpenGL code before? So, that's okay. How many of us have written C++ code before? So that is not a prerequisite for this course. We're going to spend some time this week, I think, is it this week, C++?
Yes,
yeah.
tomorrow.
Reviewing that in a session, and your first assignment will be, worthless is the wrong word, valued at 0 points, but will be a good way to get started with coding in C++ if you haven't done it before. Okay, so before I just talk at you for some time, I thought I'd involve you guys and chat a little bit. So what are the applications of computer graphics? When you guys think of graphics, what comes to mind? No, I'll speak at once. What was that? Animation, absolutely, right? Making What's with the Lamp jump around. Games, absolutely. Yes? VR, right? Virtual reality, I think is one of the new applications that's really coming back.
Data visualization?
Data visualization, absolutely. Anything else? Yeah? Simulation, yeah. Physics, I would argue that state of the art in numerical partial differential equations right now is actually in the movie effects world, right? To make one of those robots in Pacific Rim, like, splash around and presumably the Pacific Ocean is a ridiculous amount of computation and numerical things for solving Navier-Stokes equations, right? Exactly what we do, you know, to simulate fluids. Yeah? User interfaces, absolutely. Something we all take for granted is that all of your laptop screens that I see in this room are refreshing at a rate of at least 29.97 frames per second, right? That's the rate at which your eye doesn't detect that your screen is blinking images really fast, right? And as you can imagine, that produces all kinds of computational challenges, right? In fact, one of the really exciting and fun things that we'll learn in the computer graphics class is that we have a budget of time that we can spend in different parts of the graphics pipeline. Right? We can either make a really cool looking image, or we can simulate a bouncing ball really, really fast. But we can't do both, because if we do, we exceed that 29.97 frames per second, and then the guy playing the video game is unhappy. Right? And so the way that we reason about algorithms is kind of funny that way. Right? We have a budget, and we have to choose how to spend it. Any other applications of graphics? There's a couple big ones. So probably most of you guys in your pockets have some kind of phone. Yeah? And of course, hiding inside of this phone is not just a user interface, but also a camera, which is operating in real time, turning your face into like a cute Dalmatian, whatever it is that this Snapchat thing does, all in real time. And it's a great application of computer graphics technology and image processing put together. And then this semester, actually at the graduate level, the graphics class we have going on right now is in computational fabrication and 3D printing, which isn't quite computer graphics. In a sense, it's like graphics before we had, the hardware. But really, the same technology that we're using to make 3D models for rendering video games, computer-aided design, appears in that world as well, with the extra added excitement that you got to direct this machine that pees out glue to make it come out in real life. So in any event, to summarize what you guys have already shared, in this class, we're going to take a very high-level overview of some of the exciting and fun parts of the graphics world. And we're going to touch on applications that include things like movies and special effects. Probably all these images are a little dated now, right? This is Finding Nemo and Shrek. But in any event, one of the really interesting things is that if you go to the movie theater today and you see almost any film, there's a computer that was involved in almost every step of the pipeline from the camera to the screen. Right? And the fact that it's not even distinguishable, you can't even see the effects anymore, is really an amazing development in the graphics world, and one that we'll cover here. One of the fun things about movies and special effects is that computational time is less of a factor. Yeah? Finding Nemo, I believe, took many hours to render a single frame for some of the frames in the video. I actually worked at Pixar. I'm not quite that old, but I did work at Pixar not so long after that film came out. And one of the struggles that they ran into, which I thought was kind of funny, was that apparently the artists really enjoy modeling sea life swaying in the background. And so there's some frames in Finding Nemo where like one pixel has, like 15 different little ugly sea plants just like kind of gently moving around. And so if you want to just decide on the one color of that pixel, you have to do a heck of a lot of computation to like smear out all the different plants that intersect with it. And so that's the kind of thing that probably wouldn't happen in real time. And one of the really fun things is there's really more than you would expect. I mean, obviously, Finding Nemo is computer generated, but there's this whole genre of really cool YouTube videos that I encourage you guys to dig around that shows all of the visual effects that go into films as they come out. Typically, these are released with the SIGGRAPH conference, which happens in July, August. And so here's a roll from ILM. We won't watch the whole thing. But it's kind of fun just to see. They break down everything.
are still sustaining clean energy.
I love watching these things. Okay, so hopefully you guys saw that just like in a single frame of, I want to call him Captain Planet, but I don't think that's right. What's his name? Tony Stark flying around. Let's see, what all zoomed past the screen really quickly there. There was very complicated geometry that was stored on the computer. There was textures studied on top of those, and then smoke and fluids and breaking glass, and all of these things get composited together to make a single frame of one of these films. And one of the kind of fun things is that the way that the movie studios are organized in terms of like people's full-time job is roughly in parallel with the steps of the graphics rendering pipeline that we'll see here. Oh, that's changing as time moves forward. Obviously, on the other side of the spectrum is video games. So video games also have some beautiful 3D content, but here the priority is perception, right? So whereas you can spend tons and tons of time rendering every single frame of a movie, and it doesn't matter because you can play it back really quickly, here the video games have to be responsive, except maybe in a cutscene or whatever. Right? And so the types of algorithms that go into designing rendering, drawing these different scenes in simulation, is all about understanding the human perceptual system rather than simulating the real world. Right? In other words, if I do my physics poorly, are you going to notice, or are you going to be perfectly happy to suspend the disbelief and play your video game? Right? Or if I have a budget of some tiny fraction of a second, do I spend it making my AI for my game a little more advanced, or do I spend that budget, making the subsurface scattering under the water a little more realistic? Okay? And one thing that we'll learn, especially later in the semester, is that our brains have evolved all kinds of mechanisms for sort of sorting through what information is important and what information is irrelevant when we look at a scene right in front of us. And the graphics pipeline actually leverages that to put the most computational time into the things that your eye is going to notice. Right? And so once again, you can see how this is kind of different from, like, I don't know, if you go to David's algorithms class, we're not just studying big O here. The time complexity here is tangled up with like the time complexity of your neurons. Another kind of related area that's maybe a little more serious is simulation. These days, I believe, if you train to be a pilot, you spend quite some time not actually piloting an airplane, but rather piloting a virtual airplane. Personally, I find that to be a good thing. The really amazing thing here is that we've gotten so close to capturing the real world digitally that we can do that, and the skill actually transfers to putting somebody in the real world. And in fact, nowadays, some of the most important graphics technologies actually involve putting things back into the real world. Right? And here, how many of us, does anybody know what CAD stands for? Yeah?
Computer Assisted Design.
Sure, and sometimes computer aided, I never knew the difference. And anybody know what CAM? Manufacturing, exactly. Yeah, so these days, almost any product that you buy in the grocery store was probably modeled in a CAD or CAM tool before it was mass-produced. Okay. And so not only are computers enabling the cool graphics that you see on the screen, they're actually enabling the cool shapes of consumer products too, which would otherwise be extremely difficult to manufacture. And so these tools are kind of interesting because they have to, if a graphics tool is a little inaccurate, maybe it's not the end of the world. Here, after you look at it on a computer screen, you want it to capture the object you actually make as well as possible. Yeah? And related to that challenge, another big application that we'll touch upon just a tiny bit in this course, more so if you take my graduate geometry class in the spring, we'll talk a lot about architecture applications which depend on geometric algorithms quite a bit. But architecture is one of the really cool applications of ray tracing and tools that we'll talk about a third of the way through the semester here. Because oftentimes you would like, before you put millions of dollars into building something like Building 32 around the corner, you want to know what it's going to look like on a rainy day, and on a sunny day, and at 2 o'clock, and at midnight, and whatever. And if you have a 3D model of your building, you can simulate how the light is going to bounce around. And not only can you do that, you can also estimate your heating bill. Right? At the same time, it's exactly the same computation because you can figure out how much light is getting into your building and hence how much energy is getting radiated off the floor or what have you. Yeah? And in fact, there's there's some really neat architecture tools where if you're like designing your own apartment, You can place furniture in it, preview it in real time. Probably these days you can put it in VR goggles and walk around and see if it's really the layout you want before you invest time and money into actually making it. In fact, my research group has been collaborating a bit with this company Wayfair in downtown Boston. They sell furniture online. And one of the really neat things that they're developing is essentially an iPhone app where you can hold your phone up to like a corner of your house, drop in a piece of furniture that you want to buy, and kind of preview it inside of the environment. Of course, doing that is an interesting coupling between computer vision and graphics, right? On the one hand, you need to do enough computer vision to understand where the light is coming from that your camera is observing, and then you have to render the piece of furniture inside of there as well as possible. Yeah. And that relates to these VR applications, which a couple years ago when we taught this course, I think were purely science fiction. You know, these guys were advertising these. You know, I think this was a Microsoft advertisement for HoloLens before it came out. Of course, HoloLens doesn't actually do any of these things yet, but someday it will. And I think it's pretty clear at this point the technology has moved forward enough that the people in this room are likely the people that are really going to make VR a reality, right? That up until now, it's been kind of a fun toy that makes like 1 in every 10 people, myself included, a little bit seasick. But that's slowly changing, and both with kind of the evolution of hardware and software to make for usable and interesting tools, despite the fate of the Google Glass. On the scientific side, one of the things that graphics allows us to do is not just simulate the real world, but also to understand data that we normally wouldn't be able to look at. Right? So oftentimes if you go into the computational fluid dynamics world, or even these days in molecular biology, what you'll see is computer graphics really underlies a lot of the tools that they use for doing everyday science, right? And for understanding interesting structures in nature that otherwise would be very difficult to see. So for fun, I threw into our slides a recent example where some of our colleagues are working on simulating fluids, and one of the byproducts of what they do is visualization that just shows the neat structure that's sitting underneath a fluid, like these vortex rings. By the way, for your final project, don't implement this paper. I had somebody try last week. This is very difficult. But you can see that the computer graphics world not only allows you to render Tony Stark breaking through a window, but also to see the cool structures that are sitting inside of a piece of smoke as it flies forward in time. This is really amazing stuff. Let me see if I can flip forward to one of the more impressive. Man, YouTube plus PowerPoint is not a very common. There you go. One of the things that we like to do in computer graphics world is use this 3D model of a bunny quite a bit. I don't know if you caught that. And this teapot. We'll see both of those in this course. And here they splash together into a incompressible filament-based whatever fluid. And here you can see the structures that are sitting underneath it, which is really a visualization of some pretty advanced physics concepts that have only developed the last 5–10 years. One of the big examples, many of which were developed at MIT actually, are in the medical imaging world. Humans are pretty unreliable when they're doing surgery, and one of the things that we can do is help them out in various fashions. For instance, here there's some screenshots from medical imaging like MRI, where you can look into the inside of someone's brain. Extremely challenging volumetric rendering problem, right? Because now I get the density of every point in the interior of your head. But that's a whole volume worth of numbers. How do I even look at that? Is quite a challenging thing. And of course, n cubed is bigger than n squared, which is the number of pixels on the screen. And so a lot of these tools actually are right at the forefront of high-speed rendering. And there are even some really cool interfaces where maybe I have a patient lying on the counter, and rather than like using this nice flat white screen as my computer screen, I want to use their head. This particular user interface is well tuned for people like me. This poor person, it looks like they had to shave a little bit. Related to visualization, obviously education is a big one. Anybody recognize this screenshot from the upper left? I always have to put this in my slides. It's this really cool visualization of conformal geometry, but I'll save that for my class next week. One of the fun applications that I actually spent all of last summer developing is in geographic information systems. How many of you guys use like Google Maps, Waze, whatever new one that millennials are probably using that I haven't heard of? Yeah, these are all tools that are powered by computer graphics, and in this case, it's coupled with human-computer interaction. Right? If I have that thing sitting on my car's dashboard, fast rendering is maybe not a huge challenge because these are all 2D images. But I want to make it so that I can glance at it in some tiny fraction of a second and look back at the road. and get all the information that I need, right? And so this is a great example where the human aspect matters quite a bit. And also the geometric algorithms that we'll talk about in this class are relevant to things like studying landmass. I spent my summer studying political redistricting, and they use exactly the same technology there to map out your voting districts. All of these things are underlined by graphics technology. So in this class, what we'll kind of see is that there's a lot of abstraction that can happen, right? Obviously, I just hit about 10 different applications grabbed out of like the whole breadth of computation. And it might seem that if you're a software development person in each one of these areas, you guys have a totally different set of skills. One of the really neat things that's evolved in the computer graphics world is that that really isn't the case. And the reason is that we've developed really reliable computer graphics libraries that abstract away a lot of the common tasks in such a fashion that as long as you learn the basic themes and how to interact with these things, you're a pretty versatile engineer application-wise. So in this class, we'll talk about OpenGL. Irritatingly, Apple has just deprecated OpenGL, which is confusing to me because it's the standard, but they're a company and that's what happens in industry. So hopefully your assignments won't suffer from that. If they do, we'll figure it out. But anyway, OpenGL, DirectX, whatever Apple is going to bring you next, are all essentially tools that will take care of some of the low-level aspects of rendering and interaction. And then as long as you build your software on top of that, it'll run on different operating systems, different size screens, different technologies. This is very different from, for example, when I was learning computer graphics, and you had to learn about, like, well, this cable has 12 pins, and hence I have to communicate with your screen this way. Right? All of that is essentially just not something we cover in this class anymore. And this includes, by the way, not just 3D stuff, which I think is what goes through your mind when you hear a graphics class, but also 2D graphics like Adobe Illustrator, and probably the one that happens most often on your computer screen, which is rendering fonts. Yeah? Okay, so in 6A37, essentially what we're going to learn are the fundamentals of graphics algorithms, as well as a pretty good idea of how to implement a lot of the things that we just saw. When I say pretty good idea, what I mean is obviously each of these was developed by a huge studio of people working hard on an industry product. But we're going to try and see the basic themes and challenges in the graphics world so that you could go out and do any one of these very large-scale things on your own. We're going to talk about the basics of real-time rendering. The phrase real-time rendering refers to this magic number, 29.97 frames per second. Again, that's the refresh rate of your eye. And as long as you can hit that, it's suitable for interaction on your computer. Incidentally, we typically want to lowball that so that we have some space left over for all the other computation we want to do. But we'll say that for right now. We'll talk about the basics of OpenGL, which is still the industry standard, despite our colleagues at Apple. But that's not the focus in the class in the sense that we're not going to go through the whole specification and tell you every single shader commit. Although if you want to dive into that for your final project, that's great. And finally, MIT doesn't really focus in the undergrad curriculum on programming in C and C++. In graphics, that is the reality, right? These are programming languages that are a little closer to the inner workings of your computer. And since we really care about speed, those are the languages we'll use in this class. But we expect to introduce you to those in the course of instruction, right? So I strongly encourage you to take the optional assignment seriously. Just give it a try, and we'll build from there. And again, we're not going to do anything super complicated. Like, I don't even think pointers really make an appearance in this class, which is a shame. Everybody should suffer through that at least once. So things that we won't learn, just for full disclosure here, we're not going to go through a ton of different hacks at OpenGL and DirectX. The reality is in industry, people do all kinds of weird, crazy things to squeeze a little bit of extra computation out of their GPU. And largely, these things, A, they become obsolete every 18 months when NVIDIA releases a new card, and B, largely it doesn't matter anymore. That really graphics is becoming all software again. Right? Graphics has followed this kind of interesting arc, where like maybe 20 years ago you would learn how to write graphics software because all of your graphics was processed by your CPU, right? And then we introduced the graphics card into your computer, which is this dedicated unit that just does rendering, right? And probably all of you guys' computers has some form of a graphics card, either a dedicated GPU, like what NVIDIA ATI sells, or one of these Intel integrated graphics things, which is still its own little chip that's just doing graphics computation all the time. So for a while then, people in my generation learned all these crazy hardware hacks to get as close as we could to talking to that graphics card, to squeeze out all the middleman and get the most performance we could. The reality now is that the graphics hardware is so awesome that we don't have to do that anymore. And there's some really cool software tools that encapsulate some of the giant headache of communicating with the graphics part, and, which is just great for theorists like me. Something that we probably won't cover a lot of are different software packages. I know at some universities, maybe when you see graphics, you would like learn 3D Studio Max and how to animate. In this class, of course, we're in the computer science department, so we're focused on the technical aspects of building graphics tools rather than like the artistic or modeling aspects of making the animation. Again, for your final project, if you want to explore something halfway in between, you're more than welcome to do that. I think your TA, Larry, had a funny example in his course project. There was like, what, a little guy playing trumpet? Yeah. Yeah, it was like synced up with the audio. It was pretty impressive. Yeah. And you certainly won't learn artistic skills from me, but that's not what I'm thinking. Okay, so to continue covering the kind of questions that we get at the beginning of 8 through 7, in terms of how much math and prerequisites, all that kind of stuff, I do not enforce prerequisites strictly. You are welcome to take this class at your own peril. If you've never stepped in the classroom before, that's fine. Really what we're going to need in this course is linear algebra. And when I say that, I don't mean row reduction and like the little things that you do by hand in linear algebra class that have been like outdated for the last 200 years. But rather, essentially how to reason about linear algebra, right? Like what does a matrix multiply do to a vector, and how do I think about it, and these sorts of things. Right? Unsurprisingly, most of the linear algebra we'll do in this class happens in low dimensions. Yeah. How many dimensions do you guys think? 3, 4. Nah, I didn't walk into my trap. Yeah, the answer is actually 4. We'll talk a lot about projective geometry in this class. It turns out there's like kind of an interesting hack for how to deal with cameras. Right? Cameras are not linear algebra friendly in a sense. Like they foreshorten, right? Like things that are closer to you look bigger, which is not really a linear effect. And so we'll capture that using a homogeneous coordinate system that'll take care of that particular issue. In this class, we will cover some more advanced math topics. These really don't require much more than maybe calculus class. We'll talk about homogeneous coordinates, which is a fancy phrase for division, ODEs, and we'll have one lecture on sampling and anti-aliasing. I don't know if you guys know what that is. If you don't, that's fine, because that's what we cover in this class. Anti-aliasing is the fact that your computer screen is a big grid of pixels, but things you want to render typically squeeze between those pixels, right? And so there's some round off that has to happen, right, in order to decide on the color of a given pixel. So if you've used MS Paint before and drawn a diagonal line, you've probably seen this like kind of zigzaggy looking thing. Obviously that isn't too desirable, so typically in practice what we do is we say, even though we'd like a diagonal black line, probably in reality we should render it with little rows of gray pixels so that your eye perceives it as a smooth line. Right? And that idea is the idea of anti-aliasing, that a pixel summarizes a lot of stuff inside of that pixel, and we need to come up with one color that summarizes it. And in order to do that in any kind of rigorous way, you need some Fourier analysis. I realize that is not a thing that most undergrads here have covered, so we're going to do it completely pictorially and probably lose you guys all in the process. Every year I try a different lecture on this because I refuse to give it up, and we're going to try again this year too. The first year I did it, I brought my cello to class and we actually used a microphone and tried to sample it. It was a total disaster. So we probably won't do that. Okay, and one of the really nice things about math in 837 is that it's all a concrete and visual, right? That, like, unlike the linear algebra you might have seen in 1806. I hate these numbers. I don't get it. All of my undergrad education was at Stanford, and they just have like CS whatever, and that makes it way easy. But anyway, all the math here is in a visual context. So actually, I found that many of the students that came out of 8 through 7 had a little bit more concrete understanding of linear algebra. And because of that, one of the things that you'll get is a little bit of insight beyond the computer graphics world, right? I mean, essentially, to me, this is the first class where a lot of you guys will see considerations that involve double precision floating point, right? Either here or in maybe in machine learning class, where essentially we'll deal a lot with inexact math, numerical calculations, and so on, rather than just like sorting algorithms and binning stuff. And that mode of thinking is of course applicable not just to graphics, but also interpolation, learning, PDE, simulation, Monte Carlo stuff, which shows up a lot in graphical models. If you take Polina's class, and so on. Okay, so continuing our plan a little bit, like 5 minutes on administrative stuff, then we'll give you a quick overview of the semester and of the graphics pipeline by proxy, and then we'll call it in. Okay, I guess I could have introduced myself before. I'm Justin, I'll be your instructor. My office hours are 10 to 12, I know that's early. Here's the thing, it's not early. But anyway, it's early, it's not. But those are our Wednesday mornings. Your two TAs are Sophie and Larry. If you guys could stand up here, show everybody your face. Round of applause for Sophie and Larry. Yeah, so both of them are MN students. They have both taken my 837 class in the past, so they can tell you all of the things that I get wrong and how they fixed it. So their office hours are on Mondays and Tuesdays in the evening. Notice these are at different hours here and they're in the evenings. The office hours for them will be on the 5th floor Athena cluster in W20. W20?
Student Center.
Student Center, whatever, the one with the subway in it. Yeah. And my office hours will be in my office, which is 32D460, which is in this data center on the 4th floor of the east side. Yeah. By the way, that's where all the graphics vision faculty are, so you just kind of walk around the hallway there and see what everybody's up to. In terms of administrative stuff, our course has like 7 different websites because all of these tools are like useful for different things. I'm sorry. So all of the course materials, including today's slides, which are already up, are on Stellar. How many of you guys have used Stellar before? I think that's a pretty common one. Yeah, and I can put some announcements there, although most announcements and a message board will go on Piazza. I think this is a pretty common combo in MIT course. So I'll put all the slides on Stellar, and basically everything else will be on Piazza. Yeah? I registered, everybody who registered for this course, as of I think the middle of last week, I went ahead and dropped on Piazza. If you don't have a Piazza account, this is your responsibility to sign up, right? I can't like keep, I have to do it manually every time somebody drops this class, okay? In terms of grading, I know this is all the fun stuff, right? The way that this class is structured, most of your grade are the assignments. I think computer graphics is not the kind of problem where you'll be like, I don't know, held at gunpoint and asked to like, solve a rendering problem. So I don't really see the value in having like a super hard exam. So instead, we're going to value you guys completing some longer term things. The projects in this class are challenging, and so so I really encourage. I always say this, and nobody listens. I encourage you to start early. I encourage that for actually 2 reasons. One is just that like graphics is hard, and it's an interesting problem because it often fails silently. Right? I think when you take intro programming, you like get a compile error and it fails, and then you fix it, and you get another compile error, and fix it. It compiles, you run like hooray, you have your list of numbers, whatever. In graphics, you'll just get like an animated character whose arm is where his leg should be, and your job is to track down why. Right? It's actually pretty rare to have things like save faults and crashes and so on. And so debugging this is a different kind of experience that takes a little bit of adjustment. The other reason to start early is that everybody has a different computer here. One thing that has been constant in the graphics world, including when I took this class as an undergrad and all the way till now, is that it's just a giant headache to get one graphics tool to work on every computer. There's no standardization in this industry. In fact, that's sort of the competitive edge that different GPU companies have, right? It's like the latest cool feature, which of course breaks all the other features. Incidentally, this means if you work at a video game company, your life is just like terrible, right? Because you have to like, if you look at code that happens in a lot of these things, there's like, if your GPU is this, then do that. If your GPU is that, then do that, right? In this class, we're not going to even attempt to capture all of that. So instead, our standard is this. We have tested all of our assignments on Windows, Linux, and Mac. However, you are responsible for your assignments working on the Athena cluster machines on the 5th floor of W20. Everybody repeat after me. I'm going to test my assignments on the Athena cluster. If my assignments don't work on the Athena cluster, I will not receive credit. If my assignments don't work on the Athena cluster, I will not receive credit. It's impressive. Yeah, thanks, Dan. Okay, so that's going to be our policy, right? Is unfortunately there's just no tracking down like the bug on every single machine. So while these are tested, and you should be able to develop on your personal computer, There's some probability that it shouldn't, and I strongly suggest that before you click submit on your project, you just quickly either walk over or do the thing where your screen shows their screen, like a remote desktop kind of thing, just to test it out. Okay? So there will be a final open-ended project in this course. The instructions for this project are already on Stellar. So go ahead and take a look. That's going to be composed of a few different pieces. The MIT bureaucracy tells me that I need to inform you right now that the project is not optional, meaning that even if you think that the other grades you have in this class are enough to carry you to the end, you still must submit a final project. Consider yourselves disclosed. Yeah. There will be one exam in this class on November 15th in class. That's before the drop deadline, so you can kind of evaluate how well you're doing. I try not to make them too hard, and I'm going to rely on Larry and Sophie to make sure that I don't take my graduate class level. Then the other thing that we have are 10 nano quizzes. So at the beginning of roughly every other lecture, there will be just a short, like, 3 or 4 minute quiz. You'll open up your browser, click a few buttons, and be done. If you don't like to have your computer in class, that's fine. We'll give you some paper and collect your answers after. Okay, one more thing. So we have a course calendar. You don't need to write down this URL. It's linked on Stellar. So I tried to remove the calendar from Stellar so there's no confusion. I think I succeeded. But in any event, this is the calendar you should look at. It's a Google Doc. Can I click this link and maybe we'll just look at it real fast? It's going to make your laptop melt down. Yes. Oh, here he is. Sorry, I have a lot of browser tabs. Right, so here's the calendar. Along the left is the date. Here is the topic that we'll be covering that day. That is subject to change. This is largely historical from MIT, but I'm a relatively new guy, so I might play with it a little bit. The dates of the nano quizzes are marked with asterisks on this calendar. They're roughly every other Tuesday, but that gets kind of thrown off because of Thanksgiving and some other things. I'm going to try to film every lecture and put it on YouTube. The camera I have is a little unreliable. In fact, it looks like it doesn't have a red light this instant. So it may already have failed, which is fine. And you can ignore the last column, it's just for my own organizational purposes. There are 1 or 2 lectures that we'll have to have a guest because reasons. Okay. I think we've already covered prerequisites, but the more important information here is that there are 2 review sessions for those of you who either have never seen C, C++, or have forgotten your linear algebra. That's fine. Shame on you, but that's fine. So tomorrow, there's a review session. I think, is that Sophie in C++C? Larry. I'm not gonna lie, I just made a random guess. Right, so Larry tomorrow will go over the basics of C, C++. He hopefully already has slides on that, or he should borrow them from me if he doesn't. And then a week from tomorrow, on the 14th, Sophie will go over some linear algebra review. Okay? And so that way, after Larry's session, you'll have everything you need for assignment 0, which is actually due a week from yesterday. Remember that it's worth 0 credits, right? So you shouldn't be stressed out about that. It's just, at the very least, I want all of you guys to go home and click compile and run on that code, because it's going to use the graphics library that we'll be using throughout this class, so it's worthwhile just to get that headache out of the way now instead of like 5 minutes before your actual homework is due. Okay? You guys all laugh, but this is coming from experience teaching this class. I see it every year. Okay. Right, so the way that the assignments work, we want you to turn in code and an executable. Don't ask our poor TAs to compile your code. You're going to turn it in with a README file telling you if anything is broken. Just be honest about it. It's okay. And to have some nice coding style. Our assignments are cumulative in this class because you're going to be building up graphic systems, which means you might want to try and write your code carefully instead of just like a hot mess of things. Because you're going to have to deal with that hot mess for like the rest of the semester. Okay? And our collaboration policy here is that your projects are going to be submitted individually, but you should feel free to like sit with your friends and talk about it. So I think all this is pretty simple. Finally, I believe, not quite finally, almost. I'm sorry, I hate this stuff. You have some late days for late assignments. So cumulatively over the semester, we take the integral over however many days there are. You'll have 3 late days. Yes, Larry, this is different from when you took the course, because when you took the course, never mind. The instructors were still perfecting their system. Right, so you'll have 3 late days. These are measured in periods of 24 hours. They're not measured in terms of course lectures, because that's lopsided. Yeah? And these lose 25% per day additively. Yeah, this is not compound interest. So like you will get 0 credit after 4 days. Okay. Obviously, if there's an issue, you can go talk to SQ, and with their permission, you can try to come up with alternative, arrangements if you really are to miss the deadline. But really try to stay on top of this class because it's a class that builds, and it's tough if it's no builds. Your late days cannot be used for any piece of the final project. For the most part, this isn't going to matter because I'm betting you're going to use it before then anyway. But the one time where I saw this become an issue, the final project proposals are due quite close to the date of your quiz. This is the only way that I can get this semester to kind of work out numerically. That's okay, A, because we already know about it now, and B, because the proposal's like a paragraph. But just beware, you cannot use the late days, and don't come to me saying like, well, the quiz is here, so I wanted to use the late day. That's not an excuse. Cool. Okay. We already covered that. Assignments are hard. There's some more assignments we'll talk about in a second. And then finally, the final project is already up on Stellar. Essentially, it's an extremely open-ended project. What I'm going to do is ask you guys to propose a topic that you're excited about in the computer graphics world. Roughly the equivalent of 2 coding projects worth of work. You'll propose it. You can work with a partner on this one if you would like. And then you're going to essentially have a short check-in just to let us know that you've written some code. And then a presentation or write-up. I think it's pretty normal at the end of the semester. One incentive for you is that the grand prize for the best project in this class will be a free trip to SIGGRAPH. How many of us have heard of SIGGRAPH before? So this is the sort of worldwide conference in computer graphics. I think it attracts on the order of 10,000 to 15,000 people. This coming year it'll be in LA, I think. Usually, it's every other year it's in LA. So it was in Vancouver before, it must be in Yeah, so I will cover, basically out of my own research funds, a free trip to SIGGRAPH for the most interesting projects. Unless they're all terrible. I reserve. Yes? The course staff. Yeah. And it's totally discretionary and unfair. Yeah. Cool. Okay, so I think that concludes all the administrative stuff. Are there any questions about how 837 works? I think it's a pretty standard, straightforward course. We don't have a textbook in this class. There are many graphics textbooks out there. I encourage you not to look at them. they tend to be a little bit dated. This is the kind of thing that changes so much that the textbooks actually aren't super useful. Okay. Don't tell my colleagues. Right. So now let's take a little bit about the semester, which roughly is going to cover also our high-level overview of the graphics. So here's a screenshot from, frankly, I don't remember which video game, but some video game or another. And the basic question that we're going to answer in 6837 is, how do I make this image? Yeah? In particular, if I want to write a piece of software that renders this thing, how can I do it from the bottom up? First of all, if you guys look closely at this image, can you see why this is complicated? What are some interesting features in this rendered image here? Yes?
There's reflection of light from the sheet.
Yeah, there's reflection of light, right? So you're seeing indirect sources of illumination. Yes?
The whole setting is like very highly layered. So you have like a bunch of things in the foreground and
Yeah, there's a ton of interesting information, including some complicated geometry and kind of boring parts of the scene that you're going to have to run. Yes? Shadows. There's shadows, yeah. We're actually going to write shadow code as your last assignment. Yes?
The trees.
The trees, yes, the trees. The trees actually might be simple. There's a technique called billboarding, where essentially a tree is just a rendered photograph that they just slap at the background of the scene. I'm actually not sure how they rendered this particular image. But yeah, the trees might be quite complicated. Yeah?
Speaking of photo, you slap the skybox.
The skybox, yeah. There's sky behind this, and just generally there's lots of interesting texture, right? Probably these textures were actually gathered from photographs and then rendered on top of the 3D object. Anything else? Notice that the camera is kind of blurry, right? So like what objects in the scene affect each pixel is kind of a weird nonlinear thing, right? So these are all some pretty crazy things that we have to cope with. So in general, when we talk about the pipeline of just producing this one I would say, okay, scene from a video game. It's when our standards are pretty high. Involves a lot of things. First of all, it begins with geometry, right? There are a lot of very complicated 3D objects in the scene, each of which is covered with a different material and different lights. By the way, it's kind of cool. If you look at people in graphic studios, their jobs kind of look like the same as the jobs of people on a movie set, right? Like there are people whose job is to do dramatic lighting, but in a video game. But after we set up the scene, of course, the next thing we have to do is make it move. Right? So something you're not seeing in this image is that I think this, I'm a theorist, that's a tractor? This thing has a lot of moving parts, and in fact, if you want to have a realistic tractor moving around in your video game, you actually have to understand tractor mechanics and code them into your code. Yeah? My brother-in-law would kill me. And then finally, you have to actually render the scene. You have to draw it. Right? And in order to render the scene, you have to cope with lighting, shadows, textures, and so on, all in that tiny fraction of a second that you have budgeted before your eye gets upset that there's nothing in front of you. Yeah? Okay, so roughly, our semester is going to look like that. So we're going to start with the beginning of this pipeline. How do you represent and model a 2D and a 3D shape? How do you put materials on these shapes, including how do you texture them, which is kind of an interesting geometry problem. We'll talk about lighting and actually incorporate a little bit of physics, like what is the physics of light and how it bounces around the scene. Then we'll cover animation. So in this class, in your second assignment, you'll code up an articulated body, so you'll have a human-ish figure with joint angles and so on, and you realize that it's a 3D shape, then maybe, I think as an extension, you can try and make it run. And then as an advanced extension, you can make it run, and like when I run it, there's a little bit of jiggle that happens, and you can do that too. And then finally, we'll talk about rendering. It's different algorithms for going from the geometry in your scene to producing a set of pixel colors on your screen. Yeah? By the way, can you guys name the two big rendering algorithms? I'm sure you guys can. Rasterization. So that would be like roughly, manual rasterization is like that. I just drew something.
Is the other vectorization?
Vectorization will be a different way to represent the geometry in the scene. We'll cover that, I'm sure. In fact, if you look at MIT News in a few days, you'll see some research from my group on a new vectorization tool. Ray tracing, exactly. So the other way, so there's sort of two ways to make a scene, right? One of them is to draw it, and the other is to simulate the physics of light. And so the ray tracing algorithm will do that. Absolutely. And so that's our overview of this semester. We'll talk about modeling and transformations, animation, ray tracing and raycasting, which is the simplest rendering algorithm to get up and running. Then we'll try to make it fast, and we'll do global illumination. Global illumination is like I put a light on this wall and the floor gets a little brighter kind of scenario. We'll talk about textures, and then we'll go through like the GPU type graphics card and what we do to make video games really fast. Some of the topics that we'll cover here include modeling. So we'll talk a lot about curves and surfaces and subdivision. Anybody recognize this animated character here? You know his name?
Jerry.
Jerry, yes. This is from a short that was in front of some Pixar film or another. It also was the first time that subdivision surfaces were used in movies. So subdivision surface, the idea is you have a few control points, and they're controlling some smooth object underneath it. Right? So that way, you give an artist relatively few degrees of freedom to work with, but they still get a smooth surface that they can draw, right? Rather than covering a surface with millions of itty-bitty little triangles. After we talk about modeling, we'll talk about transformations, like how to go from the positions of the objects in a 3D scene to the positions of the objects on your computer screen. Right? So this involves foreshortening, like dealing with the fact that train tracks look like they're going together, and in addition to just putting them on the computer screen. And we'll talk a lot about homogeneous coordinates. Okay, so the idea of that is you're going to have x, y, z like position in 3D, and then you're going to have a fourth one, which is w. And essentially what you're going to see on your computer screen is x divided by w, y divided by w, z divided by w. And roughly the w you can think of as capturing the distance you are from the computer screen. Right? So the farther you are, right, you divide by a bigger distance and things look small. So that's the basic trick there. After that, we'll talk about animation and keyframing. One of the big developments in the animation world was the fact that, like, what would be like hella painful as an animator would be if you had to put all 30 frames a second of an animation by hand on the computer. right? So instead, what modern animation tools do is you specify a few key poses and frames, and then automatic things happen in between. And actually starting, I think, in our next lecture, we'll talk about the tools that can use for that. In particular, things like splines and interpolation, which take a few sparse data points and interpolate between them. Incidentally, if you take 6036 and do machine learning, in particular time series analysis, you'll see that it is precisely the same math. Which makes sense, right? This is time. One of the fun things about animation is how do you kind of couple that with things like expressive motion and so on. We'll talk about skinning. This is the idea that typically we represent an animated character by basically a very simple skeleton that's sitting underneath it, but that's not what we wanted to draw, right? And so you have to go from this positions of these key points to the position of every point along the surface of this pointy human guy. And doing that is an algorithm that you'll implement called skinning, which is exactly what it sounds like. Skinning is remarkably challenging, right? Because you don't just want objects to move rigidly as you move your bones around, right? Your skin is kind of glorpy, is I think the technical term. And because of that, you would like for realism to capture that in your animated characters. And to make matters worse, right, eventually your skin intersects with itself, and there's some physics that happens too, right? That it shouldn't self-intersect, which is particularly challenging. In fact, there are like many research papers in SIGGRAPH that just cover things like muscle bulge and so on, and how to get that accurate in the skinning system. And that's relevant to your structure and more. In this class, we'll talk more about physics in terms of particle systems. These are exactly what they sound like. So in video games, often what happens in physics is you take a really complicated system, you approximate it with lots of little moving points that are swirling around. Right? And so you guys will implement, I think in your third assignment, a basic physical simulation tool to simulate a piece of cloth kind of flapping around. And you use the same thing, I think, to simulate springs and maybe gravity if you feel like it. And all of these things are abstractions of the physical world. In fact, when I put together my slides here, I put physics in quotation marks. So we'll talk about smoke, wind, fire, earth, wind, fire, and water in this class a little bit. And we're not going to capture any of them particularly accurately, right? The really fun thing about doing physics in this class is that what we care about is that it looks right. Yeah? Like if you took most of the tools that are used in Hollywood and brought them to computational fluid dynamics laboratory to simulate an airplane, they wouldn't be terribly happy. That said, state of the art, especially in turbulent fluids, really is in the computer graphics world, because what motivates that research is just making really cool looking images. Right? I know that one of the very popular course projects at 837 is to make a simulation tool, particularly to simulate smoke is usually kind of the easiest one to code. And we'll cover all the machinery you need to be able to do that. But seriously guys, don't all do smoke simulation. I'm tired of grading. One of the really fun ones that I like to work on is cloth. Cloth simulation was my very first research project in computer graphics, and is an interesting problem because cloth is sort of a two-dimensional object interacting with a three-dimensional world. Okay? And so when we do the cloth assignment, you're going to have to worry about collisions between a flat piece of cloth and like a sphere, and resolving them is a challenge. Similarly, less relevant to my life is hair, but the simulation of hair is an extremely important part of the graphics pipeline. Actually, especially in the last couple of years, specifically when that movie Tangled came out, the technology actually got a lot better. Okay, right. So after we talk about modeling and physically based animation, which is our politically correct term for bad physics, we'll talk about rendering algorithms. The simplest one is called ray casting, where essentially you're going to place your eyeball in front of the computer screen. This is a simulated computer screen, of course. I'm going to draw a line from my eyeball into the world, and find the first thing that intersects, and I'm going to take his color and put it on this pixel. That's it. Now all of you guys can go home and render. That's called ray casting. And what is the time complexity? Well, every pixel has to do a for loop over every object in the scene, intersect the line with that object, and then take the closest intersection. Yeah? So this is kind of like the number of pixels times the number of objects in the scene. So that's kind of slow. Yeah? But we can make it slower by introducing ray tracing. So ray tracing is if I want to capture things like reflectance, right? Where it's not enough to just say like, oh, my eyeball hits into this object. Now I also have to figure out what color it is. And in order to do that, I have to figure out what's lighting it, right? So now I have to put another for loop inside of all lights in my scene to see which ones reach the object and then do some kind of calculation involving the BRDF. Anybody know what that stands for? Or TAs? The bidirectional reflectance distribution function. Fancy phrase for like the amount of light that bounces off of a thing. So we'll talk about that quite a bit in order to figure out how to shape this. Like for instance, you can see this whole sphere is probably yellow, but of course the top is very yellow and the bottom is kind of black. Yeah? And so that basic calculation has to happen somewhere, and that's going to require a little bit of linear algebra, like a dot product. Maybe a cross product. We do fancy changing. Okay. The ray tracing algorithm allows us to do all kinds of neat stuff, right? So here's that teapot again, but now he's reflecting probably just a big ball with the texture that's sitting around him. And these are some of the earliest graphics algorithms. In fact, something that's kind of interesting, if you look at historical graphics images, some of the really earliest ones are actually more realistic than the ones that came after, because people started thinking more about efficiency, and then they got ugly, right? If you don't care about efficiency, it's actually pretty easy to generate really realistic looking images. It's just something that you guys will see in this class. It's one of the really rewarding parts of writing a ray tracer, is that in very short order you get like really neat looking images. Of course, all the objects I've shown you so far are like kind of flat looking. The next thing to do is texture. So typically, a computer graphics system stores a texture in like a photograph, like a JPEG, and then it's wrapped around like a piece of wrapping paper around a 3D shape. Right? So we'll talk a tiny bit, I'm morally obligated because it's my research field, on parameterization, which is how to take a 3D model and like turn it into a rug so that we can store texture, right? And then more importantly, we'll talk about how to go from this boring flat hippo to this nice texture. Right? Which is going to involve, I do my ray tracing, I draw a line from my eye into the hippo. Now I have to follow the hippo into the texture plane and read off a color and put it back here. Yeah? That's going to get really complicated because let's say I have a very wrinkly hippo and I view him from a mile away. Right? What's going to start happening? Well, his texture has got all this high frequency component that I have to jam into a very small number of pixels, and oftentimes this will just create noise. Right? And so we're going to have to learn how to cope with that. And the way that you cope with that is by talking about anti-aliasing. The idea that if I want to render a diagonal line on my screen, I'd probably prefer the output on the right, the output on the left. Right? And doing that is going to require very gentle, I promise, don't get scared, I kind of like having a lot of students around, but it's going to require having to be able to understand that like a fraction of a pixel is covered by an object. And what does that mean in terms of what color you should choose? Yeah. Then, finally, we'll hit some more advanced topics, and at this point it's a little bit more of a grad deck. Okay? So here is a very famous, really boring ray traced image. Anybody know what this one's called? I'm going to keep asking even though you guys don't know the answer. Called Two Balls in a Box. Close. This is called the Cornell box. I think it's actually named after a guy named Cornell. I don't think it's actually from the university. But it's used to demonstrate all the crazy rendering stuff that can go wrong. In particular, this sphere here is refractive. I always confuse. Refraction. Yeah. Refractive. This guy is reflective. Yeah. And so underneath it, for instance, they cast shadows. They reflect light onto the walls. That's a complicated thing. This guy's refractive, so it actually takes the light from its light above, redirects it, and then puts it on the ground rather than putting it toward the camera. Okay, these are all top effects. And so to cover that, unfortunately, traditional ray tracing can't. Right? So for instance, take a look underneath this refractive ball. Right? If I draw a straight line toward the light bulb and ask, like, did this point get lit or not? That's not going to be the right calculation to do, right? Because the light that he receives actually took a nonlinear path through this piece of glass. Okay? And so to cope with that, we're going to cover some tools in global illumination. Hopefully you can see the difference here. Yeah, look underneath that ball. Keep one more time. Notice that there's now fuzzy shadows. The amount of computation that goes into that fuzzy shadow is ridiculously large. And this, it's like one of those buttons where if you download Maya and you play with it, as you should, it's free for students. If you like click the global illumination button, suddenly your code will be like, what, 100 times slower? But in exchange for that, you get fuzzy shadows. That's kind of nice. Then we'll talk about shadows in video games. This is a very different approach, right? So whereas in ray tracing, like, what's our solution to everything? It's just to like throw more rays of light around. When you talk about video games, we're going to use a really clever trick called shadow mapping. This to me, like, I have bad dreams about implementing a shadow map. So naturally, I gave it to all of you guys as your final assignment in this course. The idea of shadow is that I actually render my scene twice. First, I render it from the perspective of the light bulb, right? And why do I do that? Does anybody have any ideas? Think first. Yeah.
It's real light, it's blue.
Exactly. If I render the scene from the perspective of the light bulb, well, everything that the light sees is everything that gets lit. Yeah? And so then I do a second pass rendering from the camera position. Yeah? And now that I know where things are lit, I can draw a shadow in an accurate fashion. Yeah? So if your code from previous assignments involving like camera transformations is wrong, you'll see it here. Yeah. In really cool ways too. Like your camera will rotate this way, and your shadows will like go the other way. I like have a lot of fun debugging assignments and stuff. Okay. So that brings us to the basics of the graphics pipeline. There's basically two options that we've mentioned. One is raycasting, where I send rays into the scene. So for every pixel, I look at every object and see which one is closest. The other one is called, I shouldn't say rendering, I should say rasterization, where essentially you do the opposite. You just go down the list of objects in your scene and you draw them one at a time. Right? So doing that, it turns out is roughly what your graphics card does, because it's massively parallel, right? It's over all the pixels in the screen. But what goes wrong? Well, for instance, depth becomes a problem, right? Like figuring out what object is on the top is kind of a challenge here, because if I just render them one object after the next, what would be a bad result would be like if the last thing that I drew happened to be on the top, right? And so instead, we'll talk about an object called a depth buffer, which is going to help resolve that by actually just adding another step in your rasterization. By the way, I think the depth buffer was introduced by Ed Cowell, right, who's now one of the leaders of animations. Okay, so in the graphics pipeline, in particular in the GPU pipeline, which is the graphics processing unit, we'll talk about how to handle transformations, clipping, like how to take this cow and chop off its head because you can't see it. Rasterization, which is how to draw a triangle. Right? This cow is composed of many thousands of triangles, so if you have a piece of code for drawing a triangle really fast, then you would secretly have a piece of code for drawing a cow. And how to cope with things like visibility. And then toward the end of this class, we'll cover some high-level stuff. We'll talk about color. In particular, all of the different displays in this room probably have slightly different color gamuts. Right? So like my laptop has an LCD screen, I guess. This projector has one of those, what's the thing with the really fast spinning mirror, DLP inside of it. In the back of our room here, we have a really basic display showing the time. Don't worry, we still have a few more minutes before we get to that. Of course, all of this intersects with how your eye perceives color, which irritatingly enough is kind of linear, but it's not orthogonal. Right? You can see that your eyes are more sensitive to red and green than they are to blue, which is actually going to have an effect on the graphics panel. So for instance, if I have to render all three color channels on an image, one hack to make my code faster might be to spend less time rendering the blue channel than the red and the green. Okay, kind of sneaky. And actually this happens in some image processing. And we'll talk at a very high level about display technology. This stuff changes all the time, and frankly, I'm not the right person to tell you about it. But we'll spend one lecture kind of talking a little bit about how the hardware works, and then thanking our lucky stars that we don't have to deal with it in practice. Okay, so really quickly, let's talk about our assignments and a little bit of OpenGL, and then we'll wrap up for the day. So your assignments are as follows. We're going to start with a quick warm-up. You're all going to try it? Yeah? Nods? Yeah, cool. And then we'll do some geometry, modeling, physics, ray tracing, graphics, just like we heard about in our overview of the graphics pipeline. So in your first assignment, you're going to implement some tools for rendering curves. Right? So in particular, starting in the next lecture, we're going to talk about how to represent a smooth curve when you only have sort of a discrete set of control points. And so in your assignment, you're going to actually implement some of these models. And then you're going to take those curves and sweep them to make a 3D surface, which is the typical way to make 3D geometry in the graphics pipeline. After that, we'll talk about hierarchical modeling, including this slick animation here. So we'll talk about skinning. In particular, if we have this boring skeleton, how to go from this guy to an interesting animated character with skin and bones and so on. Okay? And of course, the basic way to do that would be to just rigidly move the different pieces of his arm independently of one another. But we're going to implement a tool that handles the transition between these in an elegant fashion. Next, we'll talk about physics. You'll implement math kind of spring network style clock simulation. I think with forward integration, we're not going to do implicit in this course. It doesn't mean anything, that's okay. Then you'll implement a ray tracer, basically from scratch for rendering. And finally, we'll do some real-time graphics, and you'll see why it's so painful to write OpenGL code. Okay? So assignment 0, just very briefly before I let you guys go, is a chance to play, just a tiny bit with OpenGL. Mostly just to get it up and running, but also just to see what graphics coding looks like. So OpenGL is a computer graphics library. It is compatible with many different programming languages, C, C++, Python, Java, I don't know, Fortran probably. But in any event, working with OpenGL is a little bit of a headache because you really are essentially just harnessing the graphics card inside of your computer. And so there's a lot of incantations you have to do to make sure that you kind of move, for example, data from your computer's memory to the graphics card memory in an efficient fashion. And getting that right is challenging. In addition to that, OpenGL has its own little programming language inside of it called GLSL. Has any of you guys written GLSL code before? This is called OpenGL shading language. And it's a little programming language for writing shaders, which are exactly what it sounds like. It's like a way to tell how to render a single pixel. And the reason why this is its own programming language, it actually gets compiled by your GPU before your graphics program starts, is that then it gets run massively in parallel. Right? I mean, think about it. Your computer screen has what, in the order of hundreds of thousands of pixels, and a shader will get run for every single one of those 30 times a second. Right? So it's a very special kind of programming. So OpenGL is essentially just an API that sends stuff to your graphics card. Beginning of the semester, we're going to use it kind of like a black box. Like mostly, we will provide you with the OpenGL code, because your job is going to be to do the kind of mathy part. And later on in the semester, we're going to have you actually write some OpenGL, which is no fun at all. So essentially, in assignment 0, what you're going to do is load a triangle mesh of the Utah teapot, which was one of the very first 3D models that was ever modeled. And then you're going to display it in OpenGL, and do some color, and a very simple, I think, interaction where you just kind of drag your mouse and it rotates. Okay. In order to do that, there's some things that you should know. Essentially, on computers, we represent 3D objects using things called triangle meshes. Triangle meshes are just huge collections of triangles, which in our class will be just 3 points in R3. If you take my class in the spring, they will be more complicated than that because, of course, many of these triangles share the same vertex. And if you're trying to like measure curvature, then like just understanding the shape is one big pile of triangles is probably not the right thing to do. But in any event, in your assignment, what you'll do is load a standard mesh format for storing this kind of model. And then you'll write some code for sending it to your graphics card, and then your graphics card will take care of rendering. Okay? So in order to do that, what you're going to have to load in is the position of every corner of every triangle, the color of every vertex. I think that'll be optional. The normal at every vertex. You guys know what a normal is? That's a vector perpendicular to the surface. This is used for lighting, right, to figure out if the surface is pointed right at the light or not. And maybe some transparency information that in this assignment that will be relevant. So again, why normals? So here is an example. So here I have a light bulb sitting right at the top of the scene, and I've rendered a sphere. And of course, from a material standpoint, this is like a little crossball, right? The whole sphere is one uniform piece of material. But of course, the colors start bright and get darker, right? In particular, they drop off, like a dot product between the direction to the light and the direction perpendicular to the surface. Right? Let's think about dot products for a second. When is let's say I have 2 unit vectors. When is the dot product the biggest? I see some hand gestures. When they're parallel, right? Where dot product looks like cosine. Yeah. And when is the 0? When they're orthogonal. Yeah. If the dot product is negative, in our purposes, you should make that 0. That's a common source of a bug. The surface doesn't get more lit if you point it away from a light. But in any event, the intensity of what your camera sees looks like the dot product between the normal and the direction to the light. Right? And this is a simple model called the inversion shading. So a very typical thing to do is just to store the normal with the 3D model. If you want to talk about how to actually find the normal per vertex on a triangle mesh, that's actually not obvious. It's a little bit of a challenge to how to do that in a stable fashion. After that, you call OpenGL and just give a giant list of all this information, and it DMAs it across from your hardware, your memory in your computer to the GPU's memory, which is like, this little piece of memory which is just whispering right into the ear of your graphics card. And so essentially you would like in writing graphics code to minimize the amount of communication between your CPU code and your GPU code, because that's typically the sort of time sink. Right? In addition, you'll tell it where the camera is, and the nice thing about OpenGL is beyond that, it just takes care of it, just draw stuff for you. So the kind of high-level pseudocode here looks like you'll set up a bunch of callbacks, like when you press the keyboard, call this function. You'll compile the vertex and fragment shaders. This is kind of an interesting aspect of graphics code, which is that your GPU's job is to compile the GLSL code. So actually shaders in video games, often like the code for the shader is hiding somewhere inside of the compiled code for your video game. This sounds super weird. And then what happens is right when your video game launches, the GPU will compile the shaders, which are the code that the GPU runs. And the reason to do that is different pieces of hardware might prefer slightly different instruction sets. And so that's the way we get around that. And then you'll have this massive for loop, which is just going to keep 30 times a second updating. It's going to update the UI, change the camera if you drag your mouse, and then draw the scene again. And if you wrote your code right, this will be fast. If you wrote it wrong, like if you send the teapot to the graphics card 30 times a second instead of once and then leave it there, then it'll grind to a halt. Yeah. Actually, probably these days, it's annoying on these computers, you probably could get away with a bug and it's still do okay. Yeah. So this is the sort of graphics pipeline, circa maybe 10 years ago, right? You had this vertex buffer, which is a piece of a piece of memory, which stores all the vertices on triangle mesh. That goes into a vertex shader, which is essentially a way to apply a camera transformation to every vertex. Then you go to assembler and rasterizer, which places all the triangles on the screen. And then that's called a fragment shader, which is roughly one shader per pixel. See, that's not quite right, to determine the color. And that goes to the frame buffer, which is this little piece of memory that's sitting inside of your laptop that your computer monitor just reads off of every once in a while and displays what you're sitting here. Yeah. You want to be very careful writing the frame buffer, because the second that you do it, shows up on the screen. Right? So you want to be slick about doing kind of one of these tricks where you maybe have two frame buffers and you flip a bit and it just goes to the other side, rather than like watching this stuff draw itself on the screen. Which you guys have probably all experienced in like a low-grade video game. It's like nothing more frustrating than watching one triangle appear on the screen at a time. Okay. I think we're low on time, so we'll probably skip this, but roughly you guys should page through the remaining slides from today's lectures to get an idea of what GLSL code looks like, and use Piazza very liberally if you get stuck to get this assignment up and running. Like our job, and it's already online. Yeah. Our task here is not to like get you upset and confused. It's to get you just upset and confused enough so that you work out the details of how to get these things up. Okay. So I think we'll maybe see like we're low in time. And one thing that you'll see even in this one assignment is that linear algebra is everywhere. Right? You've got vectors and matrices and so on, just for the world's simplest piece of graphics code. So with that, I think we'll stop for the day. I'm happy to stick around for a few minutes if you guys have questions. And other than that, I'll see you on Tuesday.